All right, guys, today we're going to introduce a new term for you guys, enthalpy. We're going to learn about what that is, and then also what is an exothermic and what is an endothermic reaction. So if you guys are feeling a little bummed out, think about this. He says, yep, the tissue's talking, that's my job. Pretty disgusting, huh? I can't think of anything more humiliating. I'm so ashamed. By the way, what do you do? He asks the toilet paper. So you guys, life's not going too well, just say, you know what? Hey, at least I'm not toilet paper, right? Maybe that'll brighten your day. The guy says, I may be rebellious, but I'm also a realist, so he got tatted on his back. I'm going to regret this when I get older, because that's the truth, guys. Careful what you permanently do, any permanent decisions you make. Okay, guys, this is what we learned, I think, last lesson. We learned about what's called specific heat, and that was the heat needed to change the temperature of 1 gram of something by 1 degree Celsius. You remember it's called specific heat because each item has its own unique specific heat value. Remember the one I asked you to remember was that for water? Water's specific heat value is 1 calorie per gram degree Celsius. That means it takes 1 calorie of heat to raise 1 gram of water by 1 degree Celsius. You guys remember we were talking about why you go to the beach and the sand gets really hot and the water's still cold even though they absorb the same amount of heat from the sun. It's because water has a relatively high specific heat, sand and metals for that matter. You guys, right? That's why you'd be reluctant on a hot sunny day to pick up a dime, off on a black asphalt because it would probably be burning hot. Metals and sand have low specific heat values. That means it requires very little heat for them to rise in temperature. So we're talking about heat. It says so far stuff is absorbed, gained, or lost heat, but what is the source of the heat? Where did the heat come from? You guys, heat always is ultimately going to come from chemical change. So you guys remember that's what chemistry is a study of. As matter changes, when matter changes, there's always an accompanying change in energy, usually in the form of heat. So we're talking chemical change, gas burning, wood burning, etc. Reactions. Let's see here. Okay. But where did the heat from the reaction come from? It was stored. You guys remember, all matter has stored energy. It's easy to think about food. We know food has energy because that's why we eat food and then we're able to utilize the energy stored in food. But all matter has energy and it's stored. We call it potential energy, okay? That potential energy is called enthalpy. So just think about it, guys. All matter has stored chemical potential energy, which we call enthalpy. Some matter is higher in enthalpy, others is lower in enthalpy. All right. So you guys, we're talking about what it's called the system and the surroundings. So think about it, in chemistry, we're dealing with chemical reactions. So if you think about your reaction substances, that's what we call the system. Essentially the surroundings, guys, that's everything else. Okay, so you got a reaction, just imagine a reaction happening, the reaction species, the things involved in the reaction are the system, everything else is the surroundings. So with that being said, we're going to introduce these two new terms to you, exothermic and endothermic. You guys think about it, if you wanted to break it down, when you think therm, what are you probably thinking about? You think a thermometer, and you guys, right, and we know, you guys know now, temperature is not a measurement of heat. You guys remember it's a measure of the average kinetic energy, but there is an association with heat and temperature, so therm probably refers to heat. And then you guys know exo, think about exo, exit. I'm looking at exit sign on my door right here. Think about like an exoskeleton, right? You guys know like lobsters and bugs have exoskeletons, right? That's why when you step on a bug, it makes a crunchy sound because its hard part is on the outside. So exo means out, exit means out. So what's exothermic? That would refer to a reaction in which heat, it's always in reference from the perspective of the system. So it's exo, heat's going out of what? The system. So that's a reaction in which this heat goes out of the system and into the surroundings. Heat released from the system to the surroundings. And then you might guess endothermic. If you could think of a term that has endo, maybe you're thinking endoskeleton. You guys think about us. You have an endoskeleton. What are we saying? We've got our soft, squishy parts on the outside and our hard skeleton is on the inside. Endo means in. So an endothermic reaction would be a reaction in which heat is absorbed by the system, so it goes into the system. See, in exothermic, heat leaves the system. In an endothermic situation, heat is absorbed by the system. So heat absorbed by the system from the surroundings. So what happens to the absorbed heat? So you guys think about it. If a reaction occurs and heat is absorbed from the surroundings, what happens to that heat energy? Remember, energy is not created or destroyed, it just changes forms. What happens to it? It changes into potential stored energy in the reaction substances. So in that case, as the reactants produce products, the products now will be, as it proceeds from the reactants to the products, well, we'll get to it when we look at potential energy diagrams. All right. So, you guys, whenever we have a delta, remember big H, you can think of big H as heat, but technically it's called enthalpy. So a change in enthalpy, so if we think about a chemical reaction, as we go from reactants to products, there's going to be a change in energy or change in enthalpy. And that's associated with bond breaking and bond forming. You guys, anytime in a chemical reaction, we're kind of jumping the gun here because we haven't talked too much about chemical reactions. But in any chemical reaction, guys, old bonds are broken and new bonds are formed. When bonds break, it requires energy to break bonds. That's an endothermic process, okay? Energy has to be absorbed in order to break old bonds. And then when new bonds form, when new arrangement of atoms comes together, heat is released. That's an exothermic process. So you guys, in any chemical reaction, both of these processes are occurring. Old bonds are breaking, new bonds are forming. So if you have a process in which more energy is given off by the formation of bonds than what was required in the breaking of bonds, then overall it's going to be an exothermic reaction. But you can also have reactions in which it requires more energy to break the bonds than energy that was given off in the formation of new bonds. In that case, the overall reaction would be an endothermic reaction. Let's look at a couple here. Well, before that, I want you to start exercising. Starts eating a donut. What are you doing? He's doing stomach stretches. Hopefully you guys do a little more exercise than that. Okay, you guys, here's a typical exothermic reaction. Okay. Right, so you guys, if I was to light paper, you guys know if I light paper and I ask you, hey, what is the paper reacting with now? You don't want to say fire. Fire is the result of the paper reacting with the oxygen. And you guys know what fire is, right? It's just light and heat energy, okay? So the paper and the oxygen reacted. You guys, what did we produce? You guys, and just for lack of better, we don't have to get exactly into it, but you might say ash. But a lot of times people forget. You guys, what else is produced whenever a carbon base, you guys know paper is organic, it's carbon based. Whenever you have a carbon based substance react with oxygen, a byproduct is also carbon dioxide. Now you guys, this is what should be new. So these are the reactants that reacted and these are the products that formed. So there was a rearrangement of atoms. Notice it has this term here, 57.5 kcals. You guys, that would be a heat unit. And you guys, in this case, you got to realize the heat unit is on the product side. And why is that? Because in the reaction, not only was ash and carbon dioxide produced, but also heat is given off. The fact that it's on the product side would indicate, that's an exothermic reaction. Heat's being given off. Well, you guys, where did that heat come from? It was stored originally in the paper and the oxygen, right? The atoms have a certain arrangement. As in paper, those are carbons, hydrogen, oxygen atoms, and then oxygen's pretty easy. And then when those rearrange, heat is given off. You notice it's on the product side. So if it's on the product side, that means it's being given off. And that's experimentally determined. So somebody might ask, well, how do we know that 57.5 kcals of heat was given off? You can remember what we could do. We talked about this before. You could actually carry out that reaction in a calorimeter. So I put my paper in here, ignite it, heat's given off. The calorimeter, primarily the water surrounding it, is going to absorb it. You remember we could use our specific heat formula, right? Basically, think about the water absorbing it. So if I have the specific heat, I can figure out how much heat the water absorbed, taking the specific heat of water times the mass of water, how much water I have, and then how much the temperature changed. Use that specific heat formula to calculate Q, which would then be the heat absorbed by the water or the calorimeter, and then theoretically, if there was no heat loss to the surroundings, that would be the heat given off by that reaction. So now you guys, I want you guys to make a little energy diagram. Notice H. Once again, you can think about that as heat. More specifically, it's called enthalpy. It's the amount of potential stored energy in the reactants or products. Okay. And don't worry about this. You could look at this as just time. But anyways, the reactants, because remember our reactants are paper and oxygen, right, that we started with. They have a certain amount of stored energy in that matter and how it's arranged. So I want you to think about if you had to predict, do the products that were formed, the ash, I'm looking down at the ash on the ground, and the carbon dioxide in the air, if I compare the products to the reactants, what do you think has more potential energy? What has more energy in it? The paper and the oxygen I started with, or the ash and the carbon dioxide I end with? Hopefully you guys would realize the reactants, paper and oxygen, are higher in energy than the products. Notice the products have a lower enthalpy. So in this case, we went from a higher enthalpy or energy reactants and produced lower energy or lower enthalpy products. The difference in the enthalpy here is what we call the enthalpy change. Whenever you have a triangle, that's the delta. Whenever you have delta, that means a change in. So a change in enthalpy. And just like you would if you had to get a change in temperature, you take final minus initial. That's what you do when you want to calculate the delta H. So it's always the final minus initial. Final is the enthalpy of my products, which in this case would be ash and carbon dioxide, minus the enthalpy of the reactants, which would be paper and oxygen. And when you do that, you know, using, like, say, that calorimeter, right? You could ultimately get a, that's how ultimately we were able to experimentally determine that that's the value. You'll notice in this case, if you calculate delta H, what kind of value would you get? Notice you got the enthalpy of the products, which is a smaller number, minus the enthalpy of the reactants, which is a larger number. When you take a small number minus a large number, what kind of number do you get? You get a negative number, less than 0. So technically we put delta H, we wouldn't just say it's 57.5, we'd say it is, oh, and when it's, we would say it's negative 57.5. So you guys, when you have the negative there, what that indicates, just think about it this way. Think about, oh, that means heat's being lost. It's negative 57.5 kcals. So the negative indicates the loss of heat. So you guys, this is typical of an exothermic reaction. So whenever you guys think of an exothermic reaction, just think about burning paper. That would probably be the easiest thing to think about. Okay. It says, according to WebMD, you have bronchitis. He said, you diagnosed me off a website? I want a second opinion. He says, well, oh, healthline.com says bronchitis also. Oh, okay. You got 2 opinions. So easy.
Are all reactions exothermic?
Are all
Well,
reactions?
think about a cold pack.
Are all reactions exothermic? You guys, I would say 99.9% of the reactions that you encounter in everyday life are exothermic. We tend to go from a high energy reactant to produce low energy products. What happens to the energy when you went from a high energy to a low energy? It's released in the form of heat. But you guys can think about a cold pack. And by a cold pack, we're not talking about just taking something from a freezer and putting it. Now you can have a cold pack like that. You guys know, I don't know if you guys have ever had packs like this that's stored at room temperature. Just be a pack like you could keep in a bag, like trainers on a sport athletic field would have these. And then you would just kind of break it. And in this case, you could break it, and you by just kind of agitating it, you'll bring 2 chemicals together such that it would actually engage in an endothermic reaction. And what would you guys associate with an endothermic reaction? Think about it. In an exothermic reaction, heat's being released. In an endothermic reaction, heat's being absorbed. So what would you guys associate with that? When you guys expect the surroundings to become cooler, right? As heat energy is absorbed from the surroundings and absorbed into the system. So you guys, this would be an example of an endothermic reaction. Normally I would carry this out in the classroom if we were here, but we've got, for example, you can bring barium hydroxide in contact with ammonium thiocyanate. Don't worry about those are kind of complex. And then you don't have to worry about what products, but basically the atoms are arranged and you form products. Main thing I want you guys to see is notice where the heat unit is in this endothermic process. Notice it's on the reactant side. It's on the left side of the arrow. What that indicates is not only do these come together, but these come together along with heat. So it requires heat energy. Where's that heat energy going to come from? It's going to come from the surroundings. So these, along with heat energy from the surroundings, produce the products. So if you see the heat factor on your reactant side, that indicates the heat is being absorbed. That would be an endothermic process. Remember, these are much less, occur much less frequently than your typical exothermic reaction. So, and once again, that's experimentally determined. If you were to carry this out in a calorimeter, remember, we could carry out the burning of paper in a calorimeter, and imagine what would you guys expect to happen to the temperature. Let's say you have this happening in a calorimeter, enclosed calorimeter. You have an original temperature. Now when you're measuring the temperature of the calorimeter, what should you find? The temperature's going up, obviously, as it's absorbing heat that was being given off from the reaction. If if you were to carry out this reaction in a calorimeter, what do you think you would find? If you were looking at your, let's just imagine it was taking place in this, what do you think you would see happening? When you expect to see the temperature decreasing. And the temperature would be decreasing because heat is being taken from whenever you guys just realize that, whenever you guys take the temperature of something, you're always measuring the temperature of the surroundings. I mean, it might seem like, that if you have it in here, you're measuring the temperature, but just realize the temperature is really of the surroundings. So, as the system is absorbing heat from the surroundings, less heat, you're going to imagine a temperature drop that would be consistent with an endothermic reaction. So if we were to do the enthalpy diagram again, so once again, the reactants in this case, barium hydroxide and sodium thiocyanate, have a certain enthalpy, a certain amount of energy associated with them. When they produce when the products are produced, the question is, are the products higher or lower in stored energy than the reactants? Hopefully you guys would realize, in this case, it's going to be higher. Well, you think about it, how did you go from low energy reactants to produce high energy products? Where did the energy come from to go from a low energy, low enthalpy situation to a high energy or high enthalpy condition? The energy came from the surroundings, so it absorbed heat energy from the surroundings, allowing it to go from a low enthalpy state to a higher enthalpy state. Once again, we can measure the delta H, that's the difference in the enthalpy between the reactants and products, and you just subtract. Just like you would if you were to get a temperature change, you would get the final temperature minus the initial temperature. And in this case, you guys think about what kind of value do you guys think you would get in this case? If you take the enthalpy of the products minus the enthalpy of the reactants, what kind of value should you get when you guys get a positive value? And what should that positive value kind of indicate? That should indicate that heat is being gained, right? Heat is being gained in our product. So the delta H in this case, I wouldn't just put 6.2, I would put positive 6.2 kcals.
This reaction absorbs energy. That's why the cold pack feels cool to the touch. The energy content of the reactants must be lower than that of the product. And delta H is a positive number to indicate that energy is absorbed.
So, right, wouldn't it make sense that we would use this type of reaction to, cool a wound to reduce swelling? Because for this reaction to occur, it has to absorb heat from the surroundings, and so it's going to absorb heat from the knee, facilitating that reaction. All right, guys, that's it for today. We'll see you next time.